In the beginning there was silence, an ancient cosmic quiet that stretched across a universe still awakening from its fiery birth. For billions of years, space expanded like a slow exhale, gentle, predictable, almost rhythmic. Galaxies drifted apart as though carried on an invisible tide, and the laws of physics, elegant and confident, guided everything with mathematical certainty. But then something changed. Something subtle at first, buried in the faint glow of distant stars, whispered a truth no one expected. The universe was not simply expanding, it was accelerating as if reality itself had stepped on a hidden cosmic accelerator. This impossibility marked the beginning of one of the greatest mysteries humanity has ever faced. Imagine looking at the night sky, unaware that the darkness between stars is growing faster every second. From our perspective on Earth, the cosmos feels eternal and unmoving, but across unfathomable distances, galaxies are racing away like embers carried by a rising wind. This acceleration is not gentle. It is not expected. It is a rebellious act committed by reality itself. Scientists once believed they understood how the universe should behave, but the cosmos, it seems, has its own script, one that bends beyond the edges of human imagination. The first clue came not as a roar but as a whisper, a faint distortion in the ancient light reaching our telescopes. That light had traveled for billions of years, crossing voids so vast they make our entire galaxy feel like a speck of dust. And within that glow was a revelation quietly unraveling the structure of our understanding. Something was pushing the universe outward with growing force, as if space itself had decided to accelerate, carrying galaxies with it. This realization shook the foundations of modern physics. For decades, scientists believed the universe's expansion should slow down over time, tugged back by gravity's persistent pull. But the data said otherwise. The universe was not slowing. It was rushing, racing, accelerating toward a future no one had predicted. It was as if the universe had turned a corner at cosmic speed, leaving our theories stumbling behind it. The emotional impact of this discovery was profound. Picture a group of astronomers staring at data that refused to fit any known equation. Their models twisted, crumbled, and collapsed under the weight of new observations. These were equations that had endured for decades, surviving experiment after experiment. Yet here, in the quiet glow of distant starlight, they were failing. Something enormous and invisible was rewriting cosmic behavior on a scale too vast to ignore. We tend to believe that science is a fortress of certainty, built from the bedrock of proven laws. But the universe is not obligated to make sense to us. It is wild, immense, and sometimes indifferent to our expectations. And in this moment, this realization that acceleration was real, the universe reminded us of that indifference. It reminded us that the unknown is not a boundary, but a vast ocean hiding continents of mysteries we have yet to discover. The acceleration of the universe is not merely a scientific puzzle. It is a cosmic warning, a signpost pointing into the fog of the unknown. Something fundamental is at work, something woven into the fabric of existence itself. Whether it is a force, a property of space, or something beyond imagination, it challenges every assumption we've held about how reality operates. Even the most brilliant minds in physics felt the tremor of uncertainty ripple through their convictions. Imagine standing at the edge of a vast cliff, staring into an abyss filled not with darkness but with unanswered questions. That is where this discovery placed humanity. Every equation we trusted, every model we refined suddenly felt incomplete. Not wrong, just insufficient, like a map that ends precisely where the most important territory begins. The universe, expanding faster and faster, seemed to be urging us deeper into the unknown. And there is something profoundly human in this confrontation with mystery. We are creatures who seek patterns, who crave understanding, who feel uneasy when the world refuses to behave. Yet the cosmos does not adapt to our emotions. Its acceleration is silent, relentless, indifferent. It does not slow to accommodate our confusion. It simply continues, pushing galaxies farther apart, stretching space like an ever-tightening drum. But within that indifference lies wonder. The acceleration forces us to ask questions we never imagined asking. What is driving this? Why now? What lies ahead if this continues unchecked? Will the universe tear itself apart, or is it evolving towards something beyond comprehension? These questions create a tension between fear and awe, drawing us deeper into the mystery. The cosmos becomes not just a physical realm but a philosophical frontier, challenging our place in it. Every time we look up, we are witnessing an unfolding story written across billions of years. A story whose next chapter is hidden in the very acceleration that defies our equations. And though we stand here, small and uncertain, the mystery calls to us. It beckons us to follow, to question, to explore. The universe is speeding up, racing toward a destination we cannot yet see. Yet even as the mystery deepens, a spark of determination rises. Humanity has always advanced by confronting the unknown, and this challenge is no different. The acceleration of the universe may defy our equations, but it also ignites our curiosity. It pushes us to build better tools, ask bolder questions, and reach further into the cosmic darkness. In the beginning there was silence, an ancient cosmic quiet that stretched across a universe still awakening from its fiery birth. For billions of years, space expanded like a slow exhale, gentle, predictable, almost rhythmic. Galaxies drifted apart as though carried on an invisible tide, and the laws of physics, elegant and confident, guided everything with mathematical certainty. But then something changed. Something subtle at first, buried in the faint glow of distant stars, whispered a truth no one expected. The universe was not simply expanding, it was accelerating, as if reality itself had stepped on a hidden cosmic accelerator. This impossibility marked the beginning of one of the greatest mysteries humanity has ever faced. Imagine looking at the night sky, unaware that the darkness between stars is growing faster every second. From our perspective on Earth, the cosmos feels eternal and unmoving, but across unfathomable distances, galaxies are racing away like embers carried by a rising wind. This acceleration is not gentle. It is not expected. It is a rebellious act committed by reality itself. Scientists once believed they understood how the universe should behave, but the cosmos, it seems, has its own script, one that bends beyond the edges of human imagination. The first clue came not as a roar but as a whisper, a faint distortion in the ancient light reaching our telescopes. That light had traveled for billions of years, crossing voids so vast they make our entire galaxy feel like a speck of dust. And within that glow was a revelation quietly unraveling the structure of our understanding. Something was pushing the universe outward with growing force, as if space itself had decided to accelerate, carrying galaxies with it. This realization shook the foundations of modern physics. For decades, scientists believed the universe's expansion should slow down over time, tugged back by gravity's persistent pull. But the data said otherwise. The universe was not slowing. It was rushing, racing, accelerating toward a future no one had predicted. It was as if the universe had turned a corner at cosmic speed, leaving our theories stumbling behind it. The emotional impact of this discovery was profound. Picture a group of astronomers staring at data that refused to fit any known equation. Their models twisted, crumbled, and collapsed under the weight of new observations. These were equations that had endured for decades, surviving experiment after experiment. Yet here, in the quiet glow of distant starlight, they were failing. Something enormous and invisible was rewriting cosmic behavior on a scale too vast to ignore. We tend to believe that science is a fortress of certainty, built from the bedrock of proven laws. But the universe is not obligated to make sense to us. It is wild, immense, and sometimes indifferent to our expectations. And in this moment, this realization that acceleration was real, the universe reminded us of that indifference. It reminded us that the unknown is not a boundary, but a vast ocean hiding continents of mysteries we have yet to discover. The acceleration of the universe is not merely a scientific puzzle. It is a cosmic warning, a signpost pointing into the fog of the unknown. Something fundamental is at work, something woven into the fabric of existence itself. Whether it is a force, a property of space, or something beyond imagination, it challenges every assumption we've held about how reality operates. Even the most brilliant minds in physics felt the tremor of uncertainty ripple through their convictions. Imagine standing at the edge of a vast cliff, staring into an abyss filled not with darkness but with unanswered questions. That is where this discovery placed humanity. Every equation we trusted, every model we refined suddenly felt incomplete. Not wrong, just insufficient, like a map that ends precisely where the most important territory begins. The universe, expanding faster and faster, seemed to be urging us deeper into the unknown. And there is something profoundly human in this confrontation with mystery. We are creatures who seek patterns, who crave understanding, who feel uneasy when the world refuses to behave. Yet the cosmos does not adapt to our emotions. Its acceleration is silent, relentless, indifferent. It does not slow to accommodate our confusion. It simply continues, pushing galaxies farther apart, stretching space like an ever-tightening drum. But within that indifference lies wonder. The acceleration forces us to ask questions we never imagined asking. What is driving this? Why now? What lies ahead if this continues unchecked? Will the universe tear itself apart, or is it evolving toward something beyond comprehension? These questions create a tension between fear and awe, drawing us deeper into the mystery. The cosmos becomes not just a physical realm but a philosophical frontier, challenging our place in it. Every time we look up, we are witnessing an unfolding story written across billions of years. A story whose next chapter is hidden in the very acceleration that defies our equations. And though we stand here, small and uncertain, the mystery calls to us. It beckons us to follow, to question, to explore. The universe is speeding up, racing toward a destination we cannot yet see. Yet even as the mystery deepens, a spark of determination rises. Humanity has always advanced by confronting the unknown, and this challenge is no different. The acceleration of the universe may defy our equations, but it also ignites our curiosity. It pushes us to build better tools, ask bolder questions, and reach further into the cosmic darkness. It lurks in the emptiness, a force that cannot be touched, seen, or measured directly, yet its fingerprints are imprinted across the entire cosmos. Dark energy, an elegant phrase hiding a profound admission. We have no idea what it truly is. To imagine it, picture the vastness of intergalactic space. Not the stars, not the galaxies, not the swirling nebulae, but the pure void between them. A darkness so deep it seems to swallow meaning itself. In that emptiness, in that nothingness, something incredibly powerful is hiding. Something capable of pushing entire galaxies apart with ever-growing speed. Something capable of rewriting the universe's fate without ever revealing its true face. Dark energy is unlike anything humanity has ever encountered. It's not a substance we can collect or a particle we can crash in a collider. It is not a field we can easily map. It is not a wave we can detect. It is, in many ways, a ghost, a presence felt only through its influence on spacetime. When scientists gave it a name, they were not categorizing it. They were marking the boundary of their ignorance with a simple label, a placeholder for a truth hidden behind a cosmic veil. To describe dark energy, imagine space itself as a restless ocean. We once believed this ocean was calm, expanding gently as it aged. But now we understand that something within this ocean stirs with a subtle yet persistent power, pushing everything outward. The farther a galaxy is, the faster it is flung away, as though carried on a tide powered by an invisible storm. It is not gravity doing the pushing, gravity only pulls. Dark energy repels. It is a force that expands space itself, stretching reality wider with every passing moment. When scientists first attempted to visualize it, they used metaphors because words failed. They imagined a pressure emerging from the void, a tension embedded in the quantum structure of spacetime, or a fluid-like essence permeating the universe. But every analogy feels incomplete, because dark energy refuses to fit inside any conceptual box. It defies intuition. It defies logic. It even defies the very equations that once seemed unbreakable. Einstein himself unknowingly brushed against the edge of this mystery when he introduced the cosmological constant, an invisible energy inherent to space. At the time, he viewed it as a mathematical patch, a correction added reluctantly to maintain cosmic stability. Decades later, the accelerating universe transformed his abandoned idea into a revelation. Could dark energy simply be the cosmological constant reborn as the ruler of cosmic evolution? Perhaps. But even that explanation feels like a shallow reflection of something deeper. To understand why, consider what the cosmological constant implies. Every cubic meter of empty space carries a tiny amount of energy. That energy does not dilute as the universe expands. It remains. And as more space forms, more of this energy emerges. That means the total amount of dark energy grows with time, like a quiet tide swelling beneath reality's surface. The image is haunting, an infinite factory of energy embedded within the vacuum, silently powering the cosmos without producing heat, light, or sound. Yet the vacuum we know through quantum physics is far more chaotic than a still ocean. At unimaginably small scales, particles appear and vanish in an endless dance. The vacuum is not empty at all, it is a seething froth of unpredictable motion. So when scientists attempt to calculate how much energy the quantum vacuum should contain, the result is catastrophic. The numbers explode into impossibility. The predicted vacuum energy is so enormous that, if correct, the universe would have torn itself apart instantly after the Big Bang. But it didn't. Instead, the real dark energy is incredibly small by comparison, yet still powerful enough to dominate cosmic expansion. This discrepancy is one of the greatest unsolved riddles in all of physics. It is as though the universe is teasing us with a solution buried behind layers of contradiction. The vacuum should destroy everything. Instead, it gently accelerates the cosmos. Something is missing in our understanding, something profound. Dark energy in its mystery forces us to confront a new kind of fear. Not the fear of danger but the fear of the unknown. The fear that something fundamental is happening right under our noses, beyond our ability to perceive. It is a reminder that the universe does not need to reveal itself to us. That the cosmos can evolve, transform, and accelerate without ever offering us clarity. And yet, within that fear lies a strange beauty. Dark energy is not hostile. It is not malicious. It is simply the universe expressing a property we have yet to understand. A property that shapes everything from the motion of galaxies to the ultimate fate of reality. To reflect on it is to glimpse the vastness of our ignorance and the depth of the cosmos we inhabit. Scientists have proposed countless interpretations. Some imagine dark energy as a field, like a distant relative of the Higgs field, that fills all space with a faint, persistent force. Others picture it as a dynamic entity, evolving over time, shifting its strength as the universe grows older. Still others propose that dark energy is a sign that our understanding of gravity is incomplete, and that we must rewrite the very laws governing spacetime. In every scenario, dark energy plays the role of a cosmic puppeteer, pulling the strings of galaxies from behind a curtain. Its influence is subtle but absolute, altering the universe on scales too vast for human intuition. It turns the cosmos into a theater of ongoing transformation, accelerating the expansion with an invisible hand. But perhaps the most unsettling truth is this: dark energy may not be a thing at all. It might be a sign that the universe itself is reacting to something deeper, something rooted in the geometry of space or the flow of time, or the unseen dimensions that may curl around our reality. If dark energy is not a force but a consequence of an unseen structure, then its mystery is even greater than we imagine. To appreciate the magnitude of this puzzle, imagine the universe as a living organism. Dark energy is its pulse, steady and growing. We feel the heartbeat but we cannot see the heart. We witness the motion but we cannot observe the engine. It is this sense of hidden power that gives dark energy its almost mythic quality, an unseen ruler shaping the cosmos from the shadows. As the universe accelerates, dark energy grows in significance. Galaxies drift farther apart, and the night sky of the distant future will become darker, emptier, and quieter. Stars will grow isolated. The cosmic web will stretch until its threads thin into nothingness. In this far horizon, dark energy becomes the dominant force of everything. It decides the universe's fate, not gravity, not matter, not stars. This is the haunting truth. Something we cannot see determines the destiny of all things. And the more we try to understand it, the more it retreats into abstraction. Dark energy is a paradox, a force we can measure only through its effects, a phenomenon we can describe only through mathematics, a presence we can feel only by observing what it leaves behind. It is both real and unknowable, familiar yet alien. The universe's acceleration is its signature. The emptiness between galaxies is its hiding place. And its nature remains the most profound enigma humanity has ever encountered. Dark energy is the phantom force that pushes the cosmos into a future no equation can fully capture. A reminder that the universe is not finished surprising us, and that the greatest mysteries often hide in the spaces we once believed were empty. For generations, humanity believed that the universe could be captured through the precision of mathematics, through symbols carved into chalkboards, through equations that echoed with elegance and certainty. These equations were more than numbers. They were stories written in logic, blueprints of reality itself, promises that the cosmos obeyed a set of rules that could be uncovered, understood, and trusted. At the center of this grand framework stood Einstein's general relativity, a masterpiece of human thought that curved space and time into a living, dynamic fabric. It was an equation so profound that it reshaped the way we see the universe, transforming gravity from a force into the very geometry of existence. For nearly a century, these equations reigned without challenge. They predicted the motion of planets, the bending of starlight, the evolution of galaxies, even the birth of black holes. Every experiment that tested Einstein's ideas, no matter how extreme, seemed to confirm them. Relativity became a pillar, so immovable that the entire structure of modern physics rested upon it. Students learned it with reverence. Scientists wielded it with confidence. Observatories relied on it to interpret the glow of distant galaxies. It was a kind of cosmic scripture, a text that bridged imagination and reality. And then the universe began to accelerate. Before the discovery of the cosmic speed-up, the equations of cosmology painted a universe that expanded but gradually slowed. This deceleration made sense. Gravity pulls. Matter clumps. The universe should feel the weight of its own content, dragging its expansion into a gentle decline. The mathematics supported this narrative beautifully. Graphs curved in predictable arcs. Models matched observations with comforting precision. The universe felt tame, understandable, almost cooperative. But beneath that sense of mastery lay an unspoken assumption that the cosmos would continue behaving according to the patterns we had already mapped. This assumption went unnoticed for decades, hidden by the smooth confidence of our equations. When physicists plotted expansion curves, they did not imagine them bending upward. When they described the future of the universe, they did not consider a future where acceleration dominated. When they thought of gravity, they thought of attraction, never repulsion. The realization that something was pushing galaxies apart shattered this quiet certainty. Equations that once felt like the heartbeat of cosmic understanding suddenly trembled with inadequacy. It was as though a flawless crystal had developed a thin, jagged crack, one that ran deeper than any superficial flaw. The acceleration wasn't just a new phenomenon to be added into existing theories. It was a violation, a challenge that struck at the very core of how we believed the universe operated. It demanded a correction not in the details but in the foundations. Imagine a craftsman who has built a magnificent instrument, beautiful, symmetrical, perfectly tuned, only to discover that the notes it produces no longer resonate as they once did. Something unseen has altered the rules of harmony. That is what scientists felt when dark energy announced its presence. Their mathematical instrument, refined across generations, suddenly felt incomplete. Einstein's equations did hold a hidden term capable of producing cosmic acceleration, the cosmological constant, but it was a term he famously abandoned, calling it his greatest blunder. Yet here it was again, resurrected by the universe itself, as if mocking his regret. The irony was cosmic. The very idea that Einstein discarded might be the key to understanding the force accelerating the cosmos. But embracing that idea did not resolve the deeper issue. The constant worked mathematically, but it didn't explain the origin of this mysterious energy. It was a patch, not a solution. The beauty of the old equations became a source of tension. They were too elegant, too complete, too symmetrical. Nature, when observed closely, seemed messier, stranger, more rebellious than those perfect symbols allowed. The acceleration revealed that the universe had been hiding layers beneath layers, truths beneath truths, waiting for the right moment to lift the veil. In university classrooms, professors found themselves answering questions they never expected. But what if Einstein was only partly right? What if gravity changes at cosmic scales? What if spacetime itself has properties we haven't discovered? These questions once belonged to speculative discussions whispered in the corners of conferences. Now they were central, unavoidable, and urgent. The mathematical models were reworked. Cosmologists added terms, adjusted parameters, stretched equations in directions they had never been pulled before. Some equations folded neatly into new shapes. Others resisted, snapping under the strain of unfamiliar forces. The acceleration required cosmology to evolve not in a single step, but in a cascade of revisions, each one pushing scientists further out onto a lake of uncertainty whose ice was thin and cracking. Yet in this fragile state, something extraordinary happened. The inadequacy of the old equations became a source of inspiration. Like artists confronting the limits of their medium, physicists began exploring ideas once considered too radical or too abstract. Quantum fields, modified gravity, extra dimensions. Concepts that lived on the margins suddenly marched into the center of scientific discussions. The old equations had built our reality. But the new universe emerging from the data demanded more. The equations weren't wrong. They were incomplete. They were a chapter, not the whole book. And that realization carried both frustration and awe. Frustration because the tools that once made the universe predictable now left us standing in uncertainty. Awe because those same tools had guided us far enough to discover the mystery they could not solve. As scientists grappled with the mismatch between theory and observation, a deeper philosophical question began to rise. Had the elegance of the equations blinded us? Had the beauty of relativity lulled the scientific world into assuming the universe was simpler than it truly is? This tension, between the certainty of mathematics and the chaos of reality, became a defining emotional force in the pursuit of dark energy. It revealed that the universe is not obligated to follow the patterns we prefer, nor shape itself according to the tidy elegance of our equations. It is a reminder that the cosmos is vast, ancient, and free, and that our understanding is always provisional. The equations that built our reality still guide spacecraft, predict the bending of starlight, and shape the architecture of modern physics. But now, in the age of cosmic acceleration, they carry a quiet shadow. A recognition that behind their brilliance lies a deeper mystery, a place where mathematics falters and the universe whispers its next revelation. There are moments in the story of science when the universe forces humanity to confront an uncomfortable truth. The rulers we use to measure reality, the models we trust, the equations we consider unbreakable, can all fail at once. The failure is not loud. It does not arrive with explosions or cosmic screams. Instead, it appears quietly, in the subtle mismatch between prediction and observation. It emerges in the haunting silence of telescopes that capture a universe behaving in ways no theory ever anticipated. In that silence, a message is written. Something is wrong. For decades, the standard cosmological model, the great tapestry woven from Einstein's relativity, quantum mechanics, and the study of cosmic evolution, served as a roadmap to the universe. Scientists believed they understood how matter clustered, how galaxies formed, how gravity sculpted the cosmic web. Every piece fit neatly into a framework that felt complete. But when acceleration entered the story, the first cracks began to spread through that confidence. It started with a single contradiction. The universe was speeding up. But contradictions rarely remain lonely. Once the first anomaly appears, others begin to take shape, rising from the data like ghosts refusing to be ignored. The models had long been trusted, but now something fundamental was out of place. An unseen force, dark energy, was altering the balance of cosmic evolution. The expansion was no longer slowing but racing. The models that once explained everything suddenly explained too little. Imagine an ancient city built on the assumption that the ground beneath it is solid stone. Architects rely on that belief. Citizens trust it. Generations build upward, confident in the foundation. But then, without warning, the stone shifts. The earth trembles. Cracks appear in the walls, thin at first, then deeper, more alarming. The city does not collapse, but its fragility becomes undeniable. That is what happened to cosmology when acceleration shattered the expectations embedded in its models. The foundation did not crumble, but it shook. The first reaction was disbelief. These equations had survived a century of tests. They had predicted black holes before we ever observed one. They had guided astronauts to the moon and spacecraft to distant planets. They shaped the GPS systems that guide our daily lives. How could they fail on a cosmic scale? How could the universe behave in a way that violated the most trusted models? To understand the weight of this revelation, imagine the daily work of cosmologists, people who devote their entire lives to decoding the universe's secrets. Their tools are equations, graphs, simulations, and theories refined across decades. When the acceleration data arrived, these tools became sources of conflict. Some models bent under the new evidence, others snapped. Theories had to be rewritten, recalculated, or discarded. The emotional toll was immense. Scientists found themselves torn between two loyalties: the elegance of their theoretical frameworks and the undeniable truth of observation. Observation always wins. But winning comes at a cost. The failure of the cosmic rulers, those models once considered precise and absolute, left a void that scientists struggled to fill. If the expansion was accelerating, what else was wrong with the old framework? What assumptions had been quietly woven into the equations that now needed to be unraveled? The breakdown spread far beyond the discovery of dark energy. It seeped into every corner of cosmology. The rate at which the universe expands, the Hubble constant, became a battleground of conflicting measurements. Two methods, both rigorous and respected, produced values that refused to agree. No matter how carefully the data was refined, the tension persisted. The universe was giving two different answers to the same question. This tension felt like a fault line running beneath the entire structure of cosmology. If the expansion rate was uncertain, then everything built upon that rate, models of galaxy formation, predictions of cosmic age, the distribution of matter, became suspect. Even the timeline of the universe, once considered solid, began to blur at the edges. The cosmic microwave background, the afterglow of the Big Bang, provided one of the strongest challenges. It painted a picture of a universe finely tuned according to specific laws. Yet, as more sensitive instruments examined this ancient light, subtle irregularities appeared. These irregularities were small but persistent, tiny fingerprints that did not match what the standard model predicted. Alone, each anomaly could be dismissed. Together, they formed a constellation of doubt. The map of the universe's largest structures, the cosmic web, added another layer of mystery. Galaxies were not clustering exactly as expected. In some regions, structures formed faster. In others, they grew slower. Something was influencing the growth of cosmic structure in ways the models could not explain. Gravity alone was insufficient. It was like watching a play where the actors follow their lines but something invisible keeps tugging at the stage curtains. The scene is correct but there is interference. The models were the script. Reality was improvising. As these cracks widened, scientists faced a difficult question. Should the models be adjusted, or should entirely new models be built? It was not simply a matter of adding a new variable. The acceleration suggested that something profound, something foundational, was missing from the equations. It forced physicists to confront the possibility that gravity itself might need modification. That Einstein, brilliant as he was, may not have written the final chapter on spacetime. For some, this possibility sparked excitement. For others, it triggered something close to grief. To question relativity at cosmic scales was to question the very identity of modern physics. It meant stepping into a wilderness without a map. And yet, the acceleration demanded it. The breakdown of the old rulers did not mean they were useless. They still worked beautifully in many contexts. They guided spacecraft. They described the behavior of stars. They explained local gravitational interactions with nearly perfect accuracy. But on the stage of the entire universe, across billions of light-years, the rules began to stretch thin. They no longer defined the full story. This tension became an emotional battlefield within the scientific community. Some believed a small adjustment would fix the problem. Others believed a revolution was necessary. Conferences turned into arenas of debate. Papers clashed, theories competed, and simulations exploded with new ideas. In this chaos, creativity flourished. The cracks in the models became windows through which new possibilities emerged. Scientists proposed new forces, new particles, new fields, new geometries. They explored the idea that spacetime might respond to energy in ways we never imagined. They questioned whether the universe might be interacting with hidden dimensions. They considered that dark energy might be dynamic, fluctuating across cosmic time. Every idea, no matter how radical, was entertained, not because the scientific world had become reckless, but because the universe had forced them into humility. Through all this, one emotion stood above the rest: wonder. Wonder that the universe could still surprise us. Wonder that despite centuries of progress, we were still standing at the shore of a vast ocean of ignorance. Wonder that the cosmos had chosen to reveal its next mystery not through violence or collapse, but through a quiet acceleration, a soft, steady push that rewrote our understanding of everything. The failure of the cosmic rulers was not a defeat. It was an invitation. An invitation to look deeper, to question harder, to embrace the discomfort of the unknown. The acceleration of the universe broke our models, but it also expanded our imagination. In the ruins of old assumptions, new ideas began to take shape. Ideas that may one day lead to a deeper, more complete understanding of reality. The universe had spoken. And for the first time in a long time, science found itself humbled, unsettled, and profoundly alive. They were supposed to be simple markers, cosmic lighthouses scattered across the universe, burning with predictable brilliance. Type Ia supernovae, the explosions of dying white dwarfs, had long been considered the most reliable standard candles in astronomy. Their brightness was so uniform, so mathematically dependable, that scientists treated them like rulers laid across the cosmos. Measure their light, calculate their distance, map the expansion. It was supposed to be straightforward. Certain. But in the quiet darkness of deep space, these supernovae ignited a crisis no one saw coming. Imagine one of these stars, a dense remnant the size of Earth but heavier than the Sun, silently orbiting its companion. It steals matter bit by bit, slowly increasing in mass until it reaches a critical threshold. At that moment, it becomes unstable. Its atoms rebel. Its core ignites in a thermonuclear flash so bright it outshines entire galaxies for a moment. This explosion sends light across billions of years, carrying secrets encoded in its brightness. That light was meant to confirm the universe's slowing expansion. Instead, it delivered a message that broke cosmology. The first unsettling hints appeared as faint anomalies. Supernovae farther away seemed dimmer than expected, not by a colossal amount but just enough to raise suspicion. A small discrepancy. A whisper of something unusual. Scientists assumed the universe's expansion had decelerated over time. But the faintness of these distant explosions suggested the opposite. They were farther than they should have been. Something had stretched the space between them and us more than predicted. The data was unsettling. It contradicted everything the models insisted should be true. Yet no one wanted to leap to conclusions. Astronomers repeated their measurements, checking for dust that might dim the supernovae. They considered errors in calibration, atmospheric distortion, even subtle mistakes in processing the images. But the pattern persisted. Each new supernova deepened the mystery. Each beam of ancient light arrived slightly fainter than the theories allowed. The sky became a battlefield of evidence versus expectation. Imagine scientists sitting around illuminated screens, the ghostly glow of distant stars reflected in their eyes. Maps of the universe spread before them, dotted with supernovae like scars of ancient cosmic violence. Every point of data was a challenge. Every new detection was a verdict. And all the verdicts pointed toward the same unsettling conclusion: the universe was not slowing down. It was accelerating. The emotional weight of this realization was immense. For decades, supernovae had been symbols of reliability. They were the cosmic truth-tellers, explosions immune to the tricks and distortions of the universe's complexity. If they were revealing an anomaly, it had to be real. Their light, having traveled billions of years, had no reason to lie. The scientists weren't merely discovering something new. They were witnessing the downfall of a belief system, one rooted in expectations about gravity, expansion, and the fate of the universe. The supernovae didn't simply start the chaos, they demanded it. Their dimness wasn't an error. It was a warning. Each explosion became a time machine, allowing astronomers to look back into earlier eras of cosmic history. And the deeper they looked, the more undeniable the message became. The acceleration wasn't a recent phenomenon, it was woven into the universe's evolution. Somewhere in the cosmic past, a mysterious force had begun pushing everything apart faster and faster. This force was subtle, invisible, but powerful enough to overcome gravity on the largest scales. Dark energy. A name born from necessity, but its nature remained obscure. The supernovae didn't merely reveal dark energy, they forced it into existence as the only explanation that fit the observations. Without them, the acceleration would have remained a theoretical possibility. With them, it became an undeniable fact. Their light carried a quiet certainty that transformed the entire field of cosmology. And yet, beneath the clarity of their message lay a haunting question. Were the supernovae truly reliable? Could something else be dimming them? Could the explosions themselves be evolving over time, changing their brightness subtly across billions of years? Could the universe be tricking us with some cosmic illusion? The tension between trust and doubt grew. Some scientists feared that relying too heavily on supernovae might lead to false conclusions. Others believed with absolute conviction that the supernova data was correct. The debate itself became a source of energy, pushing the field into deeper inquiry. In the midst of this uncertainty, the supernovae continued to shine. Their explosions echoed across the cosmos, becoming cosmic messengers that forced humanity to re-examine the very nature of reality. Each burst of light was a reminder that the universe has layers of truth hidden beneath its surface, truths revealed only to those who look deep enough and question boldly enough. These ancient stellar deaths became the spark that ignited a revolution. They showed us that the universe is not a passive stage but an active participant, evolving in ways we never imagined. Their dim light became a beacon pointing toward the most profound mystery in modern science. And even now, decades after their discovery, the supernovae continue to raise questions, teasing possibilities, hinting that the universe may still be hiding something deeper. In their flickering, fading glow lies the quiet revelation that changed everything. The cosmos is accelerating and something unseen is pushing it forward. Whether these stars revealed truth or deception is still debated, but their message has reshaped our understanding of existence. There is a strange kind of fear that comes not from what we see, but from what refuses to agree with itself. Numbers, cold, precise, emotionless, should align perfectly when they describe the same universe. Yet in modern cosmology, two sets of numbers stand locked in silent conflict, staring at one another across the cosmic divide. This clash is known as the Hubble tension, and it is more than a disagreement. It is a crack in the foundation of our understanding, a riddle etched into the fabric of the cosmos itself. To measure how fast the universe expands, scientists use two powerful methods, each respected, each refined over decades, each trusted for its precision. The first method looks outward, into the ancient glow of the cosmic microwave background, the faint radiation left over from the Big Bang. This relic light carries the imprint of a young universe, whispering information about its early rhythm and structure. From these patterns, cosmologists can calculate the expansion rate the universe should have today. The result is elegant, consistent, and deeply tied to the standard cosmological model. The second method looks inward into the nearby universe, measuring distances to galaxies using supernovae, variable stars, and other astronomical markers. These luminous objects serve as stepping stones, building a ladder from Earth to the edge of the observable cosmos. Their light tells us directly how fast space is stretching right now in the current epoch. Both methods are grounded in physics. Both are anchored in observation. Both should converge on the same value. But they don't. The Hubble tension is the widening gap between these two measurements. The early universe calculation predicts an expansion rate that is slower. The late universe observation insists the expansion is faster. No matter how many times the experiments are refined, no matter how precise the instruments become, the disagreement refuses to disappear. It grows sharper, more insistent, like a hidden truth struggling to surface. Imagine standing at a crossroads where two pathways lead into the cosmos, each beautifully paved with data, each tested with care. You take one path and discover a universe expanding at one speed. You take the other and find a universe racing faster. The difference is not small. It is large enough to demand explanation. Large enough to reveal that something about our understanding is incomplete. For scientists, this tension is not simply an intellectual puzzle. It is an emotional confrontation with uncertainty. These measurements are the cosmic rulers that map the universe's growth. If they conflict, then the map is wrong. The models built upon that map, models describing everything from galaxy formation to the age of the universe, begin to wobble. A single inconsistency ripples outward, disturbing the entire structure of cosmology. Some researchers believe the tension is a sign of new physics, forces or particles yet to be discovered, influencing the universe in ways we do not yet understand. Others suspect that the early universe behaved differently than we thought, that something exotic happened in its first moments, altering the cosmic imprint we now read in the microwave background. Still others argue that our cosmic distance ladder, trusted though it is, may hide subtle biases, tiny errors that grow into large disagreements across billions of light years. But none of these explanations has prevailed. Each new study only deepens the mystery. To visualize this tension, imagine two clocks ticking at slightly different speeds. One clock is placed in the past, frozen in the moment when the universe was a glowing fog of plasma. The other is placed in the present, among the galaxies we observe today. Both clocks should keep perfect time. Both should reflect the same cosmic story. Yet, when scientists compare them, the clocks are out of sync. Something happened in the transition between past and present. Something changed the universe's pace. And that something may be connected to the very force accelerating the cosmos. The tension creates a feeling of cosmic vertigo, a sense that the universe is slipping through our conceptual grasp. If the expansion rate is uncertain, then the universe's age becomes uncertain. If the early universe leads to one prediction and the modern universe contradicts it, then the bridge connecting them is broken. Somewhere along that bridge, a missing link awaits discovery. As the disagreement persisted, astronomers began re-examining their assumptions with growing urgency. They refined their telescopes. They recalibrated instruments. They revisited decades of data. They replaced old distance markers with new ones, layering independent methods together like threads woven into a tapestry. Yet every thread pointed to the same conclusion. The local universe is expanding faster than it should. The more precise the measurements became, the louder the tension grew. It was as if the universe was raising its voice, insisting we had overlooked something vital. Something woven into its structure. Something that might illuminate the mystery of dark energy itself. Some theories propose that dark energy was weaker in the past and grew stronger over time, creating an upward bend in the expansion curve that the early universe could not predict. Others suggest that dark matter interacts with radiation or gravity in unexpected ways, altering the expansion history. A few imagine entirely new forces, fifth forces, operating on the largest scales. Some radical models suggest the problem is not with the universe at all, but with us. Perhaps our understanding of how light travels through expanding spacetime is incomplete. Perhaps the cosmic distance ladder is built upon subtle illusions created by the shape of the universe itself. In every case, the Hubble tension acts like a beacon, pointing towards something hidden in the cosmic shadows. The emotional undercurrent of this conflict is powerful. Scientists find themselves pulled between exhilaration and frustration. Exhilaration because the tension might be a doorway to a new era of physics. Frustration because the answer remains elusive, just beyond reach. It is like hearing a faint melody coming from behind a locked door, beautiful, haunting, but impossible to decipher. The tension forces us to confront the unsettling idea that the universe may be more complex than any model we've built. The cosmos is not simply expanding, it is evolving, shifting in ways our equations strain to capture. The numbers are telling us something profound. They are signaling that the acceleration, the dark energy driving it, and the history of cosmic expansion are all part of a deeper, hidden structure. The Hubble tension is not a mathematical disagreement. It is a message. A sign that our rulers are bent, our assumptions incomplete, and our understanding only a thin layer atop an ocean of mystery. In the quiet glare of conflicting measurements, the universe is whispering that the path forward is uncharted, and that the greatest revelations may still lie ahead. For generations, Einstein's theory of general relativity stood like a mountain at the center of physics, immovable, elegant, and awe-inspiring. It shaped our understanding of space and time, rewrote the laws of gravity, and survived every experimental test we could throw at it. From the orbit of Mercury to the bending of starlight, from black holes to gravitational waves, relativity proved itself again and again. It was the closest thing science ever had to a perfect idea. And for a long time it seemed unchallengeable. But the universe has a habit of humbling even our greatest truths. The discovery of cosmic acceleration cracked open a door that had long remained sealed. Suddenly, physicists were forced to ask a question once considered nearly unthinkable. What if Einstein's theory, beautiful, precise, and triumphant, was incomplete? What if the laws governing gravity at the scale of galaxies and clusters did not hold the same way across the entire cosmos? What if, in the grandest expanses of space, gravity behaved differently? It was a question heavy with emotional weight. To question Einstein was to question the foundation of modern physics itself. It was like asking whether the earth beneath our feet might be hollow. Yet the acceleration demanded answers the old equations refused to provide. Relativity predicted a slowing universe, not a speeding one. Something was pushing spacetime outward, and if it wasn't dark energy as a simple constant, then perhaps gravity itself was changing its rules. Imagine standing before a vast tapestry woven with patterns so intricate and symmetrical that it seems flawless. Then, as light shifts across its surface, you notice small distortions, threads pulled ever so slightly, patterns that don't line up the way they once seemed to. That realization doesn't destroy the tapestry, but it forces you to question the craft behind it. That is what cosmologists felt when they first considered modifying Einstein's theory. The idea was not born out of rebellion but necessity. Observations were shouting that something fundamental was missing. Relativity explained gravity on the scale of stars and planets. It explained the motion of galaxies and the structure of black holes. But the universe itself, stretching, accelerating, expanding into the unknown, was defying its predictions. It was as though nature had quietly told us, Einstein showed you the beginning. Now continue the story. Modified gravity theories began to emerge like sparks in the darkness. Some suggested that spacetime might respond differently to different forms of energy. Others proposed that gravity could weaken across vast distances, or perhaps strengthen under certain cosmic conditions. A few even imagined that gravity was not a fundamental force at all, but an emergent phenomenon, something that arises from deeper, hidden layers of physics, the way temperature emerges from the motion of countless atoms. One of the boldest proposals suggested that extra dimensions, unseen and curled up beyond our perception, might subtly influence the way gravity operates. If gravity could leak into these dimensions or draw strength from them, the cosmic expansion might behave in unexpected ways. The acceleration could be a side effect of a geometry far grander than the one we perceive. These ideas were daring, unsettling, and breathtaking. They stretched imagination to its limits. Yet they also carried a quiet dread. Because if gravity truly behaved differently across cosmic scales, then every assumption about the universe's evolution would need to be re-examined. The age of the universe, the formation of galaxies, the distribution of matter, all might require reinterpretation. It was as if the universe had gently pulled the rug out from under us, leaving us suspended in midair, scrambling to regain balance. The emotional conflict inside the scientific community deepened. Some researchers embraced the possibility of new gravitational laws, excited by the prospect of revolution. Others resisted fiercely, protecting the legacy of relativity with near-religious devotion. To many, modifying Einstein's theory felt like vandalizing a masterpiece. To others, it felt like adding the next movement to a cosmic symphony. But science does not belong to comfort. It belongs to truth. And so the search continued. Physicists designed experiments to probe gravity on cosmic scales. They studied galaxy clusters, watched how massive structures distorted light through gravitational lensing, and examined how the cosmic web of matter evolved over billions of years. If gravity behaved differently, these structures would reveal the fingerprints of the deviation. Some results hinted at anomalies, small deviations from expectations, subtle discrepancies in structure formation, faint whispers suggesting that gravity might indeed be shifting its behavior. Other results reinforced relativity's strength, showing that Einstein's laws still held firm even across vast distances. The tension grew. No clear answer emerged. The universe seemed to be offering clues with one hand and hiding the truth with the other. It was like chasing a shadow in a dimly lit room, always present, never fully graspable. The philosophical implications were profound. If gravity could change, what else could? Was spacetime itself dynamic in ways we had not imagined? Did the universe carry hidden layers of reality, waiting for the right moment to reveal themselves? Could dark energy be a sign not of a new substance, but of an old law unraveling at its edges? Scientists found themselves standing at a precipice between the known and the unknown. Behind them stood relativity, a monument of human achievement, a theory that had reshaped the world. Ahead of them lay uncharted terrain, a wilderness of possibilities where gravity might twist in ways we had never seen. The leap into that wilderness required courage, a willingness to let go of certainty and embrace mystery. Some theories painted gravity as a cosmic storyteller, changing its narrative across time. Others described it as a holographic phenomenon, emerging from information stored at the edges of the universe. Still others imagined that gravity was a whisper from quantum reality, a bridge between the macroscopic world we see and the microscopic one we have yet to understand. In every scenario, one truth remained. The acceleration of the universe forced us to confront the possibility that Einstein's legacy, though magnificent, may be only the beginning of a deeper, more intricate truth. The cracks in relativity were not fractures of failure, but openings, windows into a realm where gravity dances to rhythms we have not yet learned to hear. The universe was calling us to listen, to question, to explore beyond the familiar elegance of Einstein's equations. And in that call there was both fear and exhilaration. Fear that the foundations of physics might shift. Exhilaration that we might be standing at the threshold of a new revolution, one that could reshape our understanding of reality just as profoundly as Einstein once did. Gravity may not be broken. It may simply be evolving. And the universe, accelerating into the unknown, is urging us to evolve with it. In the quietest regions of the universe, in the deepest pockets of what appears to be nothingness, a storm is raging. It is not a storm of wind or fire or gravity, but of restless quantum activity, an invisible turbulence woven into the very fabric of space. What we call empty space is anything but empty. It is a sea of fleeting particles, appearing and vanishing in the blink of an instant, bubbling in and out of existence. This restless dance is known as the quantum vacuum, and within it lies one of the greatest and most unsettling paradoxes in modern science. To visualize the vacuum, imagine staring into a pitch-black abyss. At first it seems silent and still. But if your vision could reach the quantum scale, you would see a chaos of unimaginable intensity. Virtual particles flicker into existence, collide, annihilate, and then reappear, like waves crashing in an endless, unpredictable rhythm. This activity never stops. It never slows. It is the background hum of the universe, the heartbeat of existence. Quantum physics tells us that every tiny region of space is filled with this seething energy. Even the void between galaxies, light years wide and colder than anything on Earth, is saturated with these fluctuations. If we could harness even a fraction of the energy inside a single cubic centimeter of vacuum, it would exceed the output of all stars in the observable universe. The vacuum should be unimaginably powerful. Yet the universe whispers a different story. When physicists attempt to calculate the amount of vacuum energy that should exist, the mathematics spirals into catastrophe. The predicted energy density is not just too large. It is absurd, ridiculous, off by a factor so enormous it defies comprehension. The theory predicts a vacuum energy 120 orders of magnitude larger than what we observe driving cosmic acceleration. It is the greatest mismatch between theory and measurement in the history of science. This is the quantum vacuum paradox. The most successful theory in physics predicts an outcome that would destroy the universe instantly, while the universe itself behaves as though almost none of that energy exists. It is the cosmic equivalent of hearing an orchestra playing softly while the sheet music insists they should be producing a deafening roar. This contradiction strikes at the core of our understanding. If quantum theory is correct, and every experiment suggests it is, then why is the vacuum so calm? Why isn't the universe exploding outward at a rate billions of times faster? What suppresses the vacuum's raw power? And if the vacuum really is filled with energy, how much of that energy is responsible for the accelerating expansion of the universe? Imagine standing on the edge of an ocean where the waves should tower like mountains, but instead they ripple gently against the shore. Nothing in the physics of waves has changed. Nothing in the laws governing water seems broken. Yet reality refuses to match the calculations. The vacuum behaves the same way. Its waves should be colossal, overwhelming. Yet they barely disturb the cosmos. Some scientists once hoped the vacuum energy might cancel itself out through mathematical symmetry. Perhaps positive and negative contributions balanced with perfect precision, leaving only a tiny residue behind. But this balance would require a fine-tuning so exact it strains belief, like arranging two numbers so precisely aligned that their difference begins at the 120th decimal place. Nature rarely engineers such coincidences. And yet, if this is what the vacuum is doing, it is a miracle of cosmic restraint. Others propose that we misunderstand the nature of the vacuum entirely. Perhaps vacuum energy interacts with gravity in a way we do not yet grasp. Maybe it is not energy in the conventional sense at all, but the result of a deeper structure hidden beneath spacetime, something quantum theory only glimpses but cannot fully describe. Some even suggest that dark energy is simply the vacuum energy behaving differently over time, slowly revealing itself as the universe expands. If the vacuum is dynamic, not static, then the acceleration may be a symptom of its evolution, a soft tremor from the quantum world scaling upward into the cosmos. This question, what is the true energy of the vacuum, carries a chilling emotional weight. If the vacuum is stable now, could it destabilize one day? Could a shift in the quantum landscape unleash the full force of the vacuum, rewriting physics in an instant? Theoretical physicists consider this possibility in hushed tones, calling it vacuum decay, a process that could reshape the universe at the speed of light. It is not likely. But the fact that nature even permits the idea reveals how fragile our reality might be. Yet not all implications lead to fear. The paradox also ignites wonder. It suggests that the universe is built upon a foundation we cannot yet perceive, an invisible architecture of laws and interactions that lie beyond our reach. The vacuum is not empty. It is not simple. It is a labyrinth of energy, structure, and mystery deeper than human imagination has ever ventured. And the acceleration of the universe may be the first faint clue that something extraordinary is happening in those unseen depths. The more we observe the cosmos, the more the vacuum reveals its fingerprints. The subtle push of dark energy may be nothing more than the vacuum's quiet assertion of influence. Not the roaring ocean predicted by calculations, but a gentle tide, barely detectable, yet powerful enough to reshape the destiny of galaxies. In the quantum vacuum paradox, we find a fracture in the bridge connecting the smallest scales of reality with the largest. It is a reminder that our theories, magnificent though they are, do not yet converge. A reminder that the universe still guards its secrets with layers of contradiction, inviting us to peel them back one by one. Something is hidden in the emptiness. Something is waiting in the silence between particles. Something in the vacuum knows the answer to the greatest mystery of all. Why the universe is speeding up, defying every equation we thought we understood. There are moments when science reaches so far into the unknown that it brushes against the edge of imagination itself. The accelerating universe forced physicists to confront a possibility once whispered only in speculative corners of theoretical physics, that our cosmos may be just one of many. A single chapter in a library of universes. A lone bubble drifting in a cosmic ocean filled with countless others. This idea, the multiverse, was once a fringe concept, a mathematical curiosity with no foothold in observation. But when the universe began speeding up for reasons no known force could explain, the multiverse suddenly transformed from a philosophical dream into a scientific escape hatch. Imagine the universe not as a singular entity, but as a vast landscape of possibilities. A terrain where different regions follow different physical laws, where the constants of nature, mass, charge, gravity, even the speed of light, shift like patterns in a kaleidoscope. In such a landscape, dark energy might not be a mysterious force but a simple byproduct of where we happen to live. One valley in the cosmic terrain may produce a universe with strong dark energy, another may produce none at all. Our universe could be just one pixel in an infinite cosmic mosaic. This idea did not arise from desperation alone. It emerged from the mathematics of inflation, the theory describing how the universe expanded unimaginably fast in its first tiny fraction of a second. Inflation was initially proposed to solve several puzzles: the flatness of the universe, the uniformity of cosmic microwave background radiation, the absence of magnetic monopoles. But as physicists studied it more deeply, inflation evolved into something far stranger. It suggested that inflation might not have been a one-time event. Instead, it may still be happening, in pockets of reality far beyond our cosmic horizon. If inflation never truly ends, it spawns bubble after bubble, each containing its own universe with its own properties. Some bubbles expand into existence and collide. Others drift apart forever. Our universe would simply be one of these bubbles, floating in a sea of eternally inflating space. In this scenario, dark energy is no longer a fundamental mystery. It is an environmental condition, a cosmic climate unique to our bubble. The acceleration of our universe becomes not a universal truth, but a local phenomenon. The emotional impact of this realization is profound. If the multiverse is real, then everything we consider fundamental, our laws of physics, our cosmic history, our structure of space and time, might be nothing more than a regional rulebook. The universe we study with such devotion could be a single grain of sand on an endless beach. This thought evokes both wonder and existential unease. It is thrilling to imagine infinite universes, each with its own nature. Yet it is unsettling to consider that our universe, with all its beauty and mystery, may not be special at all. The multiverse offers an elegant explanation for dark energy. In most universes, the vacuum energy might be too strong or too weak to allow galaxies to form. In many, the expansion might tear particles apart before atoms can stabilize. In others, gravity may overpower expansion, collapsing everything before stars can ignite. Only in a small subset of universes, an incredibly narrow band of possibilities, does the vacuum energy take a value that allows stars, planets, and life. Our universe may simply be one of the rare ones where the numbers line up perfectly. This reasoning is known as the anthropic principle. Not that the universe is designed for us, but that we naturally find ourselves in a universe where existence is possible. It is not a comfortable explanation. It denies us the satisfaction of discovering a precise equation that determines the value of dark energy. It suggests that dark energy might not be calculable at all, that it is not a fundamental constant, but an accident of cosmic geography. And yet, for all its discomfort, the multiverse provides an escape from the crushing paradox between theory and observation. If countless universes exist, then dark energy's tiny value might not be mysterious. It might simply be inevitable that one universe out of many would have such a value, and we live in that one because we couldn't exist in any of the others. But the multiverse raises a haunting question. If other universes exist, can we ever see them? Can we observe their effects? Or are we forever trapped inside our own cosmic bubble, unable to look beyond its walls? Some theories suggest that universes might collide, leaving faint scars on the cosmic microwave background, circular patterns or distortions imprinted in the sky like the fingerprints of another reality brushing against ours. Researchers have searched for these patterns, scanning the oldest light in the universe for hints of collisions. So far, the evidence remains ambiguous. A few tantalizing anomalies have sparked debate, but nothing definitive. Other theorists propose that tiny fluctuations in quantum fields, relics of the inflationary multiverse, might subtly influence the structure of matter in our universe. If these fingerprints exist, they are faint and easily lost in cosmic noise. Detecting them requires instruments far beyond our current capabilities. This leads to a philosophical tension that scientists rarely speak aloud. What if the multiverse is real but forever beyond testability? What if it explains dark energy perfectly, yet leaves us with no way to prove its existence? That possibility turns scientific exploration into a maze, with no guarantee of escape. Still, the idea persists. In part because the multiverse aligns gracefully with mathematics. In part because it resolves contradictions without contorting existing theories. And in part because, deep down, humans have always sensed that reality may be far larger than what we see. Consider the Copernican revolutions. First, the Earth was dethroned from the center of the cosmos. Then, the Sun became just another star. Then our galaxy became just one among billions. Each time, humanity felt the sting of demotion, and each time reality grew more wondrous. The multiverse is the next step in that progression. It is the ultimate dethroning, proposing that our entire universe is just one of many. It strips away the final illusion of cosmic centrality. If this is true, then the accelerating universe takes on a new meaning. It is not a cosmic catastrophe or an inexplicable force. It is simply the environment of our bubble, a reflection of the physical constants that happen to exist here and nowhere else. Yet there is something poetic in this idea. Something beautiful. It suggests that creation is not singular but abundant. That reality expresses itself in countless forms. That the cosmos is a symphony played not by one universe but by an infinite orchestra. Still, a whisper of doubt lingers. A quiet ache. Because while the multiverse explains much, it leaves us yearning for something tangible. A sign. A clue. A shadow of another universe passing by. Some evidence that we are not alone in the cosmic sea. Until that day comes, If it ever does, the multiverse remains both revelation and refuge. A dazzling hypothesis standing at the intersection of science and philosophy. A reminder that the accelerating universe may be part of something far grander than we can imagine. And in its vast, silent possibility lies one of the greatest questions ever asked. If our universe is only one bubble in an eternal cosmic ocean, what lies beyond our horizon waiting to be discovered? In the vast darkness between galaxies, beyond the glittering spirals of stars and the glowing filaments of cosmic gas, something unseen may be shaping the universe with a quiet, relentless force. Not dark matter, whose gravitational pull we infer through the motion of galaxies. Not dark energy, the mysterious push accelerating cosmic expansion. Something else. Something hidden. Something that leaves no trace except in the way the universe moves and evolves. These hypothetical influences, unknown fields, exotic particles, or entirely new forms of energy, linger like shadows behind the cosmic curtain, silently sculpting the fate of everything. Imagine walking into a room where furniture has been moved, where objects tilt in directions they shouldn't, where patterns feel wrong, but no one is there. No footprints. No fingerprints. Just the unmistakable sense that something unseen has acted. That is how physicists feel when they examine the universe's acceleration. The effects are undeniable, yet the source remains invisible. Dark energy is the prime suspect, but it may not be acting alone. There may be hidden forces influencing the expansion, forces we have not yet recognized or understood. One possibility is the existence of new scalar fields, smooth, expansive energy fields stretching across the universe. Unlike the electromagnetic field, which oscillates and creates light, these fields are silent and subtle. They do not vibrate with energy or produce radiation. Instead, they hover in the background, influencing gravity with a faint but persistent push or pull. Some physicists imagine them as cosmic fog, everywhere, undetectable but powerful enough to alter the behavior of spacetime itself. In certain models, these fields evolve over time, changing strength as the universe ages. They could have been weak during the early cosmos, almost invisible, only to rise and influence billions of years later. This evolution could explain why acceleration began when it did. Not too early to prevent galaxies from forming, and not too late to escape detection. It hints at a purposeful timing, as though the universe activated a hidden mechanism precisely when it was ready to reveal a deeper layer of truth. Another idea suggests that unknown particles swarm through the cosmos like drifting embers. These particles would be lighter than anything known, so light they barely interact with matter. They would slip through the densest clouds, pass through stars without slowing, and glide through planets unnoticed. If enough of these particles exist, their collective effect could alter the expansion of the universe. They would act as a kind of cosmic pressure, gentle but omnipresent, affecting the cosmic destiny subtly, continuously. These particles might even form entire dark sectors, worlds of matter and energy coexisting with our own but completely separated except through gravity or other weak interactions. Just as our visible universe contains complex structures, stars, galaxies, planets, so might these dark sectors contain their own variations of structure, invisible to us yet entangled with the geometry of spacetime. Their hidden activity could create ripples and distortions, influencing the expansion without ever touching our world directly. The emotional impact of these possibilities is profound. It suggests that the universe we see, magnificent as it is, might be only a fraction of the full cosmic reality. That the visible stars, galaxies, and nebulae form a thin surface layer, beneath which a deeper and more mysterious universe lies hidden. This idea evokes both wonder and an unsettling sense of incompleteness. If hidden forces exist, then our cosmic maps are missing entire continents. Some theories go even further, proposing that these hidden forces are not separate components of reality but distortions arising from the shape of spacetime itself. Perhaps spacetime has folds or twists we cannot perceive. Perhaps there are subtle geometrical properties, curvatures, symmetries, or topological features that influence the expansion like invisible levers. In this picture, the universe is not being pushed by a new force but guided by the deeper architecture of reality. This concept is difficult to visualize, but imagine a sheet of fabric stretched in multiple directions. To someone standing on the fabric, watching objects move, the motions might seem driven by mysterious pushes and pulls. But from a wider perspective, everything is controlled by the shape of the fabric itself. Our universe may be just such a fabric, its expansion guided not by a tangible force but by the hidden geometry of higher dimensions or deeper laws we have not yet uncovered. The search for hidden forces is not simply academic. Physicists design experiments with breathtaking sensitivity to detect any hint of these invisible influences. They watch for subtle deviations in galaxy clustering. They study how light bends around massive objects, searching for anomalies that shouldn't exist. They look for slight shifts in the cosmic microwave background, wrinkles in the afterglow of the Big Bang that might betray interactions with unknown energies. So far, the signals remain faint, ambiguous, and tantalizingly close to noise. But this is often how great discoveries begin, not with a roaring revelation, but with whispers that grow louder as instruments improve and theories evolve. Some researchers imagine that hidden forces might reveal themselves indirectly through small cracks in established laws. Perhaps gravity behaves differently in regions of low density. Perhaps light curves slightly more or less than relativity predicts when passing through cosmic voids. Perhaps certain particles travel in ways that hint at unseen companions influencing their motion. Each anomaly would be a clue, a trail of breadcrumbs leading deeper into the forest of the unknown. Others focus on the idea that hidden forces might be detectable through their decay or transformation. If these forces arise from fields or particles that slowly evolve, then signs of their transformation might appear in the patterns of cosmic acceleration. The acceleration itself could fluctuate subtly over billions of years, leaving a trail of evidence woven into the large-scale structure of the universe. The emotional tension surrounding these ideas is palpable. On one hand, the existence of hidden forces could solve multiple cosmic mysteries at once: dark energy, dark matter anomalies, the Hubble tension, and more. On the other hand, proving their existence requires overcoming technological limits and conceptual boundaries that challenge the very edge of human capability. But this is what makes the pursuit so thrilling. The possibility of hidden forces transforms the universe from a silent expanse into a dynamic theater of unseen interactions. It suggests that cosmic acceleration is not a simple phenomenon but a conversation among energies and structures we do not yet understand. It evokes the feeling of standing before a locked door, hearing movement behind it, sensing presence without visibility. And it raises a haunting question: are we alone in the visible universe, or are we living in a cosmic ecosystem filled with unseen companions, fields, particles, and forces that shape our destiny from the shadows? The acceleration of the universe may be the first clue that something far more elaborate is happening beneath the surface of reality. Something woven into the dark, the empty, the silent. Something hidden, waiting to be uncovered. Time is supposed to be the most dependable dimension in the universe, steady, predictable, a silent river carrying every moment from past to future. It governs the aging of stars, the decay of particles, the ticking of clocks. We trust it completely. Yet, when scientists confronted the accelerating universe, an unsettling idea began to surface. What if time itself is not behaving as we expect? What if the cosmic speed-up is not driven by a mysterious force, but by the shifting flow of time? At first glance, the idea seems impossible. We're conditioned to believe that time moves at a constant rate everywhere. A second on Earth is a second in a distant galaxy. But relativity already shattered the illusion of universal time. Gravity slows time. Motion stretches it. Time bends, warps, and flexes depending on where you stand. If time is flexible, then its behavior at cosmic scales might be far stranger than anything we experience in our local world. Imagine the universe as a colossal clockwork, each galaxy a cog turning within a grand mechanism. For billions of years, the mechanism ticks at a steady pace. But what if, without warning, the tempo begins to shift? What if the cosmic clock speeds up, not dramatically but subtly, imperceptibly? From within the system, everything appears normal. Stars shine, planets orbit, people live and die, unaware that the river of time beneath them is flowing differently. But from the perspective of cosmic history, this shift would make the expansion appear to accelerate. Not because galaxies are being pushed outward, but because time is stretching the story forward faster. To visualize this, imagine watching a movie that gradually increases its frame rate. The actors move quicker, scenes change faster, and the pacing accelerates, even though nothing within the story itself has changed. If time is accelerating, our measurements of cosmic expansion would reflect that shift. We would interpret the universe's motion as speeding up, even though the underlying dynamics remain the same. This simple but profound idea opens the door to a new interpretation of cosmic acceleration, not a force acting on space but a transformation in time. Some physicists propose that the fabric of time could be influenced by the density of energy in the universe. As galaxies drift apart and space becomes emptier, time might loosen its flow, stretching more easily across the cosmic landscape. In this scenario, time was once tightly wound, moving slower in the dense early universe. As the cosmos expanded and thinned, time relaxed, flowing more freely. This relaxation could mimic the effects of dark energy, making expansion appear to accelerate. Others imagine that time might have a hidden structure, a geometry that changes with the universe's evolution. Just as space can curve, twist, and expand, time might also possess curvature or tension. If that tension changes, the ticking of cosmic time could shift in ways we cannot directly perceive. Time might not be a dimension that simply runs. It could be an elastic medium that stretches under certain conditions and contracts under others. The emotional impact of such ideas is profound. If time is dynamic, then our experience of reality becomes even more fragile. We are not merely drifting through the universe. We are suspended within a temporal flow that may be shifting around us, invisible and untouchable. It evokes a sense of cosmic vertigo, a realization that the very foundation of experience may be evolving while we remain unaware. This possibility forces us to confront an unsettling contrast between the human scale and the cosmic scale. In our daily lives, time feels absolute. We remember. We move forward in a single direction. But on the scale of galaxies and billions of years, time may twist in ways that defy intuition. What feels steady to us may be fluid when viewed from the universe's perspective. Astronomers began searching for clues. If time is misbehaving, the patterns embedded in ancient light, the cosmic microwave background, might carry traces of this temporal distortion. The spacing of galaxies across the cosmic web could reveal unexpected irregularities. The rhythm of pulsars, the brightness of distant explosions, even the distribution of matter might hint at a deeper temporal shift. So far, the clues remain ambiguous, subtle enough to provoke curiosity but not strong enough to offer certainty. Some researchers suggest that time's behavior might be connected to unknown quantum processes. At the smallest scales, time might flicker or fluctuate, creating cumulative effects across cosmic distances. Tiny irregularities, meaningless in isolation, could scale upward into grand distortions of cosmic expansion. If time is supported by a quantum foundation, then its flow may not be smooth at all, but granular, jittering at imperceptible intervals. Others take an even more radical view. Perhaps time is not a fundamental aspect of the universe, but an emergent property, something that arises from deeper processes, the way temperature arises from the motion of atoms. If that is true, then cosmic acceleration might be nothing more than a reflection of these deeper processes' shifting state. Time would not be malfunctioning, it would be evolving. What makes this idea haunting is that we have no direct instrument to measure the behavior of time itself. All our observations rely on the flow of time as their backbone. If time changes, our tools change with it. We cannot step outside time to observe its motion. We are immersed in it completely, like fish unable to perceive the currents that govern their world. And yet, the accelerating universe may be whispering that time is not what we think. That the river we drift upon has bends we cannot see, currents we cannot sense, and tides that quietly shape the cosmic story. If time is misbehaving, then the acceleration is not a push from an unseen force. It is the universe's way of revealing that the most fundamental dimension we experience is far more mysterious than we ever imagined. In this possibility lies both fear and beauty. Fear because the familiar becomes uncertain. Beauty because the universe grows deeper, richer, and more intricate than our previous understanding allowed. The cosmic speed-up might not be a sign of dark energy at all. It might be the trembling of time itself, shifting in ways that beckon us toward a deeper truth hidden beneath the surface of reality. There are moments in science when doubt becomes a doorway, when the realization that something might be wrong opens the path to deeper truth. The accelerating universe forced physicists to question everything, but one unsettling idea lingered beneath the surface. What if the acceleration itself is an illusion? What if our cosmic rulers, our measuring sticks, our clocks, our assumptions about distances and brightness and cosmic motion, are all slightly off? The possibility that the universe is not accelerating at all, but that our measurements are flawed, shook the scientific world as profoundly as the discovery of acceleration itself. This is the essence of the cosmic clock conspiracy, the idea that the universe may not be changing, our understanding of measurement might be. Imagine building a map of a vast, ancient forest using only the flicker of lantern light. Each tree you measure seems consistent, each distance seems reasonable, each direction appears reliable. But then, after years of mapping, you begin to notice inconsistencies. Some paths appear longer than they should be. Others seem shorter. Your map starts to warp, stretch, and curl around errors you cannot see. You wonder if the forest is changing, or if the lantern's glow has been misleading you all along. That is the situation cosmologists found themselves in when they questioned the tools they used to measure the universe's expansion. The notion that measurement itself might be flawed is not new in science. Historically, almost every major scientific revolution began with the discovery that our tools or assumptions were incomplete. But applying this idea to the universe's expansion carried a haunting implication. If our cosmic measurements are wrong, then the last few decades of cosmology may have been an elaborate illusion. The suspicion began with supernovae, the ancient detonations used as standard candles to measure cosmic distances. If these explosions evolved over billions of years, shining slightly differently in the distant past, then their dimness might not signal acceleration. It might simply reflect changes in their behavior. Perhaps the stars that created them were different. Perhaps the chemical composition of early galaxies influenced the brightness. Even a tiny shift, just a few % difference, could mimic the effects of cosmic acceleration. Astronomers debated these possibilities intensely. Some argued that the early universe's stars contained fewer heavy elements, which could subtly alter the explosion. Others pointed out that dust, tiny grains floating between stars, might dim light more than expected. If the dust in early galaxies had unusual properties, it could make distant supernovae appear fainter, tricking us into thinking the universe is accelerating. But supernovae were only the beginning. Attention soon turned to the cosmic distance ladder, the intricate chain of measurements linking nearby stars to distant galaxies. From parallax to variable stars to supernovae, each rung of the ladder depends on the reliability of the previous one. If even one rung was slightly mismeasured, the entire ladder could warp. A small systematic error could stretch or compress our view of the cosmos, rewriting the story of expansion. Even light itself came under scrutiny. As photons cross billions of light-years, they pass through intergalactic gas, magnetic fields, and the subtle curvature of spacetime. Could these interactions distort the light in ways we haven't accounted for? Could the universe be scattering, absorbing, or modifying light differently than we expect? If so, our readings of distance and brightness could be skewed without us even realizing it. Then came a deeper, more philosophical suspicion. What if timekeeping itself, our cosmic clocks, is flawed? When we look at distant galaxies, we see them as they were billions of years ago. If the physics governing time or light differed in the past, even subtly, then the universe's expansion history could be misinterpreted. The cosmic clock conspiracy suggests that some hidden variable, some unrecognized shift in the behavior of time, light, or matter, could be distorting our observations. One of the most unsettling possibilities is that fundamental constants, like the speed of light or the gravitational constant, might not be truly constant over cosmic time. If they changed even slightly, the equations used to measure expansion would warp. The apparent acceleration could be a reflection of shifting constants, not a new cosmic force. Scientists tested these ideas with intense scrutiny. They measured atomic spectra from distant quasars, looking for shifts in fundamental constants. They studied ancient starlight, comparing it to modern light. They analyzed the cosmic microwave background, searching for any sign that the physics of the early universe differed from today's. Most results pointed to stability, but not with absolute certainty. The door remained slightly open. Another angle of suspicion came from cosmic structure formation. If galaxies clustered differently than expected, our interpretation of distances could be skewed. The accelerated expansion might simply reflect our misunderstanding of how matter spreads across the cosmos. The mathematical models used to reconstruct distances, especially those relying on statistical averages, could contain hidden biases. Some researchers proposed even more radical ideas. Perhaps the universe is not uniform. Maybe we live inside a large cosmic void, a vast underdense region that expands faster than the surrounding universe. If true, our measurements might reflect local expansion, not universal acceleration. This void model would explain much without requiring dark energy. But it demands a strange coincidence, that Earth occupies an unusually special location in the cosmos, a notion many scientists find philosophically uncomfortable. And yet, even discomfort does not eliminate the possibility. What makes the cosmic clock conspiracy so emotionally powerful is the way it forces us to confront our own limitations. Humans have always measured the universe indirectly. We infer distances from light, time from vibration, expansion from patterns. We do not touch the cosmos, we interpret it through tools and symbols. If those tools are flawed, then our understanding becomes a house built on shifting sand. Scientists fear this possibility not because it threatens their theories, but because it threatens the reliability of their perception. It suggests that the universe might not be accelerating, we simply might not be seeing clearly. Our cosmic rulers could be miscalibrated. Our clocks could be drifting. Our assumptions could be incomplete. Yet underneath that fear lies a spark of hope. Because if measurement errors are responsible for the apparent acceleration, then the universe may be simpler than we think. Dark energy might not be a mysterious force rewriting the laws of physics. It could be a mirage born from the limits of our observation. But if the cosmic clock conspiracy is false, and the acceleration is real, then the universe is whispering a deeper truth. Our assumptions are breaking because reality is stranger than our understanding. Either way, the path forward demands humility. The universe does not bend to our expectations. It reveals itself slowly and often in ways we least expect. The cosmic clock conspiracy remains one of the most haunting possibilities in modern physics. A reminder that even when we stare into the deep abyss of the cosmos, we might not be seeing the full picture. Something may be hiding not in the universe itself, but in the way we measure it. For centuries, humanity clung to a comforting idea that the universe is unified, governed by a single set of laws that apply everywhere and everyone. Physics, as we know it, is built upon this principle of universality. The constant speed of light, the strength of gravity, the behavior of matter, these rules were assumed to be identical across all of space. The cosmos, in this view, is a grand cathedral with perfect symmetry, every stone laid by the same blueprint. But the accelerating universe has forced us to consider a far more unsettling possibility. What if the universe is not uniform? What if different regions obey different laws? What if reality itself is fractured? Imagine traveling across unimaginable distances, past galaxies, past clusters, past the great filaments of the cosmic web, into regions so distant that their light has barely begun its journey toward us. We assume these distant realms are governed by the same physics that operates here. But what if they aren't? What if the universe is a patchwork, composed of cosmic districts where the rules of nature differ ever so slightly? In one region, gravity might be a bit stronger. In another, the speed of light might vary. In yet another, dark energy might exert a different influence. These variations, subtle though they might be, could reshape the entire expansion history of the cosmos. The idea is not as far-fetched as it first seems. Even on Earth, physical conditions vary: pressure, temperature, density, and these variations shape local phenomena. A storm forms here, a drought forms there, each responding to local conditions while the underlying laws remain the same. But what if the universe operates on a similar principle, except that the variations extend not just to conditions but to the laws themselves? What if the cosmos is a landscape of shifting physical constants? Some physicists propose that the constants we consider fundamental, such as the fine structure constant, the gravitational constant, or the mass of the electron, might not truly be constant. They might drift slowly across space or change subtly over cosmic time. If so, then the acceleration we observe could be a reflection of these shifts, not a single universal force acting uniformly everywhere. The cosmic speed-up might vary across the universe, accelerating faster in some regions and slower in others. The universe would not be a synchronized clockwork but a collection of mismatched gears, each ticking at its own pace. The emotional impact of this idea is profound. It challenges the deep human desire for order, symmetry, and universality. If the universe is fractured, then the notion of a single cosmic truth dissolves. We become inhabitants of one region among many, each with its own rules. Our understanding of physics becomes local, not universal. This realization can be unsettling, like discovering that the ground beneath your feet is just one small island in a vast archipelago of shifting terrain. Yet there is also a strange beauty in this fragmentation. A fractured universe would be a richer, more diverse cosmos than we ever imagined. Instead of a single uniform reality, the universe would be a grand tapestry of variation, an endless array of cosmic environments, each sculpted by different laws and forces. In such a universe, the acceleration we observe might be just one thread in a much larger pattern, one clue in a puzzle spanning regions we will never see. One of the most compelling pieces of evidence for a fractured universe comes from the cosmic microwave background. This ancient light, released when the universe was only 380,000 years old, is not perfectly uniform. Subtle temperature fluctuations appear across the sky, tiny variations that reveal the seeds of future galaxies. But deeper analysis has uncovered anomalies, hemispherical asymmetries, unexplained alignments, and regions of unusually low temperature. These irregularities might be statistical noise, but they might also hint at a universe where different regions followed slightly different cosmic histories. Another possible hint comes from the distribution of galaxies. Surveys of large-scale structure reveal patterns that do not always align perfectly with predictions. Certain regions of space appear to be expanding slightly faster or slower than expected. Some voids are deeper than our models predict, some clusters more massive. These anomalies could simply be random variations, but they could also reflect deeper differences in the underlying laws of physics across space. Theoretical models offer further support. In many versions of inflationary cosmology, the theory describing the universe's rapid expansion shortly after the Big Bang, different regions exit inflation at slightly different times or under slightly different conditions. This creates a cosmic quilt of patches, each with its own initial conditions and potentially its own set of physical parameters. If these differences persisted, even subtly, they could produce a fractured universe whose expansion rates vary across space. More radical theories suggest that the universe might be composed of domains separated by subtle boundaries, cosmic membranes where physical constants shift. These boundaries might be impossible to detect directly but could leave indirect signatures in the motion of galaxies or the distribution of dark matter. In such a universe, we might occupy a domain where dark energy takes a specific value, while other regions follow different trajectories. The emotional resonance of this idea extends beyond science. A fractured universe evokes themes of isolation, diversity, and cosmic identity. It challenges our assumption that the universe is a single coherent entity. It forces us to consider that our cosmic story may be just one chapter in a vast library of differing realities. It casts the acceleration of our region not as a universal phenomenon but as a local behavior shaped by our specific cosmic environment. Yet despite its unsettling implications, the fractured universe idea also offers potential solutions to some of cosmology's deepest mysteries. It could explain the Hubble tension, the mismatch between expansion rates measured in different ways. It could account for anomalies in large-scale structure. It could even provide a new perspective on dark energy, suggesting it might not be a fundamental force but a regional property of spacetime. If the universe is fractured, then we are explorers trapped within one district of a cosmic metropolis, able to observe our own streets in exquisite detail, but forever unable to see the full architecture of the city. Our measurements, our theories, our interpretations might reflect only the physics of our local domain. And that realization forces a profound humility. The acceleration we observe may not be a single cosmic truth but one perspective among many, shaped by the hidden structure of a universe more varied than we can imagine. Somewhere beyond our horizon the rules may shift. Time may flow differently. Gravity may behave strangely. Dark energy may take on forms we have never considered. The universe might be unified in ways we cannot see, or fractured in ways we are only beginning to glimpse. Either possibility deepens the mystery. Either possibility expands our sense of wonder. And both remind us that the accelerating universe is not merely a puzzle of physics, but a doorway into a cosmos far stranger, more complex, and more beautiful than we ever dreamed. Far beyond the reach of any telescope, beyond the shimmering arcs of galaxies and the faint glow of cosmic dust, the universe is racing toward a destiny no one fully understands. Its future is a story still unwritten, a tapestry woven from possibilities as terrifying as they are awe-inspiring. For most of human history, people assumed the cosmos was eternal and unchanging. Then we discovered expansion. Now we know that expansion is accelerating. With that revelation came a haunting realization. The universe is not just evolving, it is rushing toward an ending we cannot prevent. And that ending could take forms far stranger than our ancestors ever imagined. To imagine the universe's fate, picture yourself drifting through a cosmic ocean stretching endlessly in every direction. Galaxies float like islands, glowing faintly in the quiet dark. Over billions of years, these islands recede farther and farther away from one another, the ocean expanding under some invisible pressure. The emptiness grows. The silence deepens. The universe becomes a place of increasing separation, where the distances between galaxies swell like rising tides. This vision marks the beginning of the most traditional cosmic ending, heat death. Heat death is not a violent catastrophe. It is a slow, inevitable surrender. As the universe expands, energy becomes more diluted, stars burn out, and galaxies fade. The cosmic temperature drops toward absolute zero. Over incomprehensible timescales, black holes evaporate, particles decay, and even atoms may fall apart. The universe approaches a state of perfect uniformity, no gradients, no motion, no life. A silent, endless darkness. A final stillness. Yet the accelerating expansion adds a chilling twist. In a faster accelerating cosmos, galaxies will drift so far apart that they vanish from each other's view. Their light will never reach one another again. Civilizations in the far future will look into the sky and see nothing but the stars of their own galaxy, unaware that a vast universe once surrounded them. The cosmic web will unravel, leaving each galaxy stranded in its own island universe. Heat death becomes not just a fading of energy, but a cosmic isolation so profound that even the grand structure of the universe dissolves. But this is only one possible ending. There is another, far more dramatic scenario, a fate called the Big Rip. In this vision, the universe does not simply expand faster. The acceleration grows without limit, driven by a dark energy that strengthens over time. The expansion becomes so violent that it tears the cosmos apart piece by piece. First, galaxy clusters drift away. Then galaxies themselves are ripped from one another. Stars are pulled from their orbits, planets torn from stars, moons stripped from planets. Even atoms cannot withstand the force. Space expands so rapidly that the bonds holding particles together are stretched past breaking. Reality unravels at the smallest scales. In the final moment, spacetime itself is shredded. The universe ends not in darkness, but in a catastrophic explosion of expansion. Where heat death is a whisper, the Big Rip is a scream. Yet another possibility lies in the opposite direction. The universe may not accelerate forever. Dark energy might evolve, weaken, or eventually reverse. In this scenario, expansion slows, stops, and then reverses, pulling everything back inward. The cosmos collapses under its own weight in a cosmic implosion known as the Big Crunch. Galaxies collide, stars are crushed, and spacetime folds inward like burning paper. Temperatures rise to unimaginable levels until the universe is a single point of infinite density, a mirror image of the Big Bang. The end becomes the beginning. The universe dies into a seed from which a new universe could be born. This idea leads to an even more intriguing possibility: cosmic rebirth. Some theories suggest that the universe might undergo endless cycles of expansion and contraction, each ending giving birth to a new beginning. Like a cosmic heartbeat, reality pulses eternally. Each cycle may reset the laws of physics, reshaping the universe anew. Perhaps our universe is just one beat in an infinite rhythm. Perhaps countless universes came before and countless will follow. These scenarios paint radically different visions of cosmic destiny: slow fading, violent destruction, implosive collapse, eternal rebirth. Yet they all hinge on one thing: how the acceleration of the universe evolves. And that evolution remains one of the greatest uncertainties in all of science. To understand these potential fates, imagine holding a compass that points not north, but toward the future of the cosmos. But the needle spins, quivers, hesitates. It cannot settle on one direction because the laws guiding cosmic evolution are still partly hidden. The universe stands at a crossroads where small changes in dark energy's behavior determine everything. Its strength, its constancy, its interaction with gravity, all these factors could push the cosmos toward any of these endings. Some physicists propose that dark energy may decay over time, like a radioactive substance losing potency. If so, the acceleration might slow and stabilize, avoiding both heat death and the Big Rip. Others suggest dark energy might oscillate, rising and falling in cycles that correspond to phases of cosmic growth and contraction. Still others imagine that dark energy is not a substance at all, but a sign that spacetime itself is evolving in ways we do not yet understand. The emotional resonance of these possibilities is profound. Each one forces us to confront our fragility. Our galaxy, our solar system, our planet, all become temporary objects in a universe whose scales dwarf our imagination. And yet, within that humility lies something beautiful. The universe invites us to imagine futures beyond our lifespan, beyond our species, beyond the boundaries of our entire cosmic story. The future fate of the universe is not merely a distant, abstract question. It reflects the deepest mysteries of physics: the nature of dark energy, the structure of spacetime, the fate of matter, the rules governing cosmic evolution. To contemplate the end of the universe is to confront the limits of human understanding and the vastness of what remains unknown. But these possible endings also speak to something deeply human. They remind us that everything changes, that the cosmos itself evolves, transforms, and ages, that even the universe, with all its grandeur, is not eternal. And yet, there is a strange comfort in knowing the universe has a destiny. Whether it fades into quiet darkness, tears itself apart in a moment of cosmic violence, collapses into rebirth, or cycles forever, the universe is telling us a story, one larger than any star, larger than any galaxy, larger than any species that might rise or fall within it. The accelerating universe is the first chapter of this final saga. It is the whisper that something monumental lies ahead. It is the clue that the cosmic engine driving reality is far more complex than we imagined. And in that whisper we sense both fear and wonder. Fear because the universe's fate may be beyond our ability to comprehend. Wonder because we are here, right now, alive at the moment when humanity first glimpses the future of everything. The universe's final fate is a mirror held up to our own existence. It reflects our curiosity, our limitations, our courage to ask questions whose answers may not arrive in our lifetime. And as we stare into the cosmic future, we stand in awe of a universe that is evolving, accelerating, and guiding us toward revelations yet to come. In its possible endings, the universe reveals its true nature, not as a static backdrop to our lives, but as a living, changing entity with a story of its own. And that story, whether it ends in silence, fire, collapse, or rebirth, is still unfolding across the vastness of space, inviting us to imagine what lies beyond the horizon of time. When the universe revealed that it was accelerating, scientists were not the only ones shaken. Philosophers who have long wrestled with questions of existence, meaning, and reality, found themselves pulled into a cosmic mystery that reached far beyond physics. The accelerating universe did not simply challenge mathematical models, it challenged assumptions about our place in the cosmos. It forced humanity to confront questions older than science itself. What does it mean to live in a universe that is not stable, not eternal, not predictable? What does it mean when the future stretches toward an ever-growing emptiness? Imagine a philosopher standing beneath the night sky, gazing into the darkness between the stars. To the physicist, that darkness is a data set. To the philosopher, it is a mirror. The accelerating expansion becomes not only a scientific puzzle but a source of existential tension. If the universe is destined to drift apart, if galaxies are fated to disappear beyond the cosmic horizon, then the cosmos becomes a stage where everything is slowly vanishing. This perspective sparks a deep, ancient unease, the fear that existence itself is slipping away from our understanding. Since ancient times, humans have sought patterns that reveal cosmic order. Philosophers believed that the universe must follow principles of harmony, balance, and reason. But the accelerating universe disrupts this narrative. It suggests disorder at the deepest level, an expanding chaos driven by something we cannot see, detect, or fully describe. This forces us to confront the possibility that the universe is not built on human logic. It may be shaped by principles beyond interpretation, leaving us forever on the threshold of understanding. The acceleration raises profound questions. Is meaning tied to the structure of the universe? Does the cosmic future have anything to do with our human search for purpose? If everything moves farther apart, does meaning too begin to stretch and thin? These questions are unsettling because they strip away the comforting illusion that the universe is designed to be understood. Instead, they present a cosmos indifferent to comprehension, a universe that evolves according to laws that may be forever hidden from human intellect. For philosophers grappling with the nature of time, the acceleration poses another challenge. Time is not merely a backdrop against which events unfold. It is active, dynamic, woven into the expansion itself. As the universe accelerates, time shapes cosmic history in ways that defy intuition. What does it mean for time to be tethered to expansion? Is time a fundamental dimension or merely an emergent illusion? These questions take philosophy into realms once reserved for physics, creating a merging of disciplines that blurs traditional boundaries. Some thinkers view the accelerating universe through the lens of existentialism. If the cosmos is ultimately drifting into silence, then meaning cannot be found in the universe's destiny. Meaning must be created locally within the human mind and experience. In such a universe, purpose becomes an act of rebellion against the cosmic void. The very act of seeking understanding becomes meaningful precisely because the universe offers no assurances. Others take a more mystical approach. They imagine that the accelerating universe reflects the deep strangeness of reality, a reminder that existence is not bound to human expectations. From this perspective, acceleration becomes a symbol of mystery, a sign that the cosmos is larger, richer, and more unknowable than conventional thinking allows. It encourages humility, inviting humans to embrace the unknown rather than fear it. Still others ponder the moral implications of cosmic acceleration. If the universe is expanding into emptiness, then life becomes a rare phenomenon, a fragile spark in an immense, growing darkness. This raises questions about responsibility. If life is rare, then perhaps we have an ethical duty to preserve and cultivate it. The accelerating universe suggests scarcity on a cosmic scale, and scarcity often gives rise to value. Under this view, consciousness becomes precious not because the universe is meaningful, but because meaning is manufactured by conscious beings. Yet the most haunting philosophical question may be this: is the universe comprehensible at all? For centuries, human progress was fueled by the belief that reality could be understood through reason, observation, and logic. The accelerating universe challenges that belief. It hints at deeper layers of reality, forces, fields, or principles, hidden beneath the surface. If dark energy is beyond our grasp, if acceleration is a symptom of something we may never detect, then perhaps the universe contains truths that human minds are not equipped to grasp. This idea is both terrifying and liberating. Terrifying because it suggests limits to knowledge. Liberating because it frees us from the expectation of total understanding. It allows us to exist in a universe filled with mystery, without demanding that every mystery be solved. The philosophical response to cosmic acceleration is not a single viewpoint but a spectrum, from dread to wonder, from humility to curiosity. Some see the acceleration as a sign that the universe is slipping away, unraveling into incomprehensibility. Others see it as an invitation to expand human thought, to build new frameworks that can hold the weight of cosmic strangeness. In either case, acceleration is not merely a physical phenomenon. It is a philosophical revelation, a cosmic riddle that forces humanity to rethink its assumptions about reality. In the end, the accelerating universe confronts us with a simple but profound truth: we are not merely observers of the cosmos, we are participants in its mystery. And as the universe races forward into an unknown future, our search for meaning races alongside it, driven by the same eternal desire to understand who we are, where we come from, and what role we play in a universe that may never fully reveal itself. The universe may be accelerating, but humanity is not watching passively. Across mountaintops, frozen deserts, and orbits above Earth, a new generation of instruments is awakening, machines of unimaginable precision, built for one purpose: to expose the cause of cosmic acceleration. These telescopes, satellites, detectors, and observatories represent a revolution in our ability to interrogate the universe. They are humanity's most ambitious attempt to reach into the darkness and demand an answer from the cosmos itself. Imagine standing inside a massive observatory dome as the roof slowly opens, revealing a sky scattered with billions of stars. The air is thin and cold, the machinery humming softly like a mechanical heartbeat. This is where humanity confronts the unknown, not with fear but with curiosity sharpened into technology. The next generation of experiments will look deeper, farther, and more precisely than anything that came before. They will test hypotheses about dark energy, hidden forces, modified gravity, and the structure of spacetime itself. The age of mere speculation is ending. The era of direct investigation is beginning. One of the most ambitious tools in this revolution is the Vera C. Rubin Observatory, home to the Legacy Survey of Space and Time, LSST. This colossal camera will capture the entire visible sky every few nights, creating a dynamic map of the universe that evolves in real time. It will track billions of galaxies, millions of supernovae, and countless cosmic events, each one a potential clue about the nature of acceleration. If dark energy evolves over time, or if unknown forces shape cosmic structure, LSST will reveal subtle patterns in the movements of galaxies and the brightening and dimming of distant stars. High above Earth, the Euclid mission drifts silently in space, scanning the universe with unprecedented clarity. Its instruments will measure how galaxies stretch and distort the light that passes through them, mapping the invisible scaffolding of dark matter. By studying how this structure changes across cosmic time, Euclid will test whether dark energy behaves like a constant pressure in the vacuum or something more dynamic. If the acceleration wavers, strengthens, or weakens even slightly, Euclid will detect the shift. Then there is the Nancy Grace Roman Space Telescope, a powerful eye designed to survey enormous swaths of the cosmos with extraordinary precision. Roman's wide-field instruments will measure the shapes and distances of galaxies billions of light-years away, searching for tiny deviations that might signal the presence of new physics. It will observe distant supernovae with unmatched accuracy, probing whether they truly behave as standard candles, or whether their brightness hides complexities that could reshape our understanding of cosmic expansion. But telescopes are only part of the experimental revolution. Experiments like the Dark Energy Spectroscopic Instrument, DESI, are mapping the positions of millions of galaxies, tracing the cosmic web like a cartographer mapping the oceans. By studying the distribution of galaxies at different distances, DESI can reconstruct the expansion history of the universe. It is as if scientists are listening to the heartbeat of the cosmos, looking for irregularities in its rhythm. Meanwhile, gravitational wave observatories like LIGO, Virgo, and the upcoming LISA mission add an entirely new dimension to the search. Gravitational waves carry information not just about space, but about spacetime's deepest fabric. If dark energy interacts with gravity in unexpected ways, these waves may stretch or compress differently than predicted. By listening to the cosmic symphony of colliding black holes and neutron stars, scientists may detect distortions that hint at hidden forces or modified gravity theories. Each of these instruments offers a different perspective, a unique angle from which to examine the mystery. But together they form something far more powerful, a worldwide network of cosmic detectives, each gathering clues from different wavelengths, different depths, and different eras of the universe's history. Their combined data may finally illuminate the darkness that has shrouded the cause of cosmic acceleration for decades. The emotional energy inside this scientific revolution is unlike anything seen since the discovery of the expanding universe itself. Scientists feel a mixture of excitement and tension, as though standing at the edge of a cliff overlooking a vast landscape of new knowledge. Every new dataset brings the possibility of anomaly, of deviation, of a hint pointing toward a deeper truth. The air in research centers around the world feels electric, charged with anticipation. The stakes are immense. If dark energy is a constant, the universe races toward heat death. If it strengthens, we may face a big rip. If it weakens, a cosmic collapse could occur billions of years from now. If hidden forces or extra dimensions are responsible, then our entire understanding of reality may be incomplete. If time itself is shifting, then the very foundation of perception must be reconsidered. Each potential answer carries consequences not only for cosmology but for physics, philosophy, and the human sense of place. But beyond the scientific implications lies something deeply human. These instruments represent our species reaching upward, refusing to accept ignorance as destiny. They are monuments of curiosity, proof that even as the universe rushes outward, humanity pushes forward. In the face of mystery we build tools. We gather light from across billions of years. We listen to ripples in spacetime. We refuse to let the darkness remain silent. In these new observatories, reason and wonder meet. Precision and imagination collide. Each telescope, each spectrograph, each detector is an extension of the human mind, reaching across the cosmic gulf with a single question. Why is the universe speeding up? And as the data arrives, slowly at first, then in torrents, it feels as though the universe is finally beginning to answer. Not with clarity, not yet, but with hints, patterns, whispers embedded in starlight and gravitational waves. The revolution is only beginning. The tools are awakening. The search is intensifying. Somewhere out there, buried in the darkness between galaxies, hidden in the structure of spacetime, or encoded in the glow of ancient light, lies the truth behind cosmic acceleration. And humanity, armed with the most ambitious instruments ever built, is closer than ever to discovering it. Stand at the edge of human knowledge, and the universe stretches out before you like an infinite ocean of unanswered questions. Every discovery we make illuminates a small circle of understanding, but the moment that circle expands, the surrounding darkness grows even larger. The accelerating universe is one of those discoveries, one that widened our knowledge and deepened our ignorance at the same time. It is a reminder that no matter how far we reach, the cosmos remains vast, ancient, and filled with secrets we can scarcely imagine. Imagine floating in deep space, surrounded by galaxies drifting silently in all directions. Each galaxy is a book in the cosmic library, its pages written in the language of light and gravity. For centuries we've learned to read those pages. We've deciphered the life cycles of stars, the structure of atoms, the geometry of spacetime. But the acceleration of the universe is a sentence written in a script we do not yet understand. It stands like a boundary, the point at which human comprehension begins to falter. This boundary is not sharp, it is soft, shifting, and alive. It moves forward as we advance, yet always stays just out of reach. We chase it only to realize it has moved again. This chase defines the human spirit. We are creatures who explore, who question, who refuse to accept the limits nature presents. Yet the accelerating universe challenges us with a humility we rarely confront. It shows us that even our most elegant theories, relativity, quantum physics, thermodynamics, are incomplete chapters in a story still unfolding across cosmic time. At this edge of understanding, the universe feels both familiar and alien. The stars we see are comforting, constant, ancient companions. But beyond them lies a truth we have only glimpsed, a truth that fractures the idea of a predictable cosmos. The acceleration hints at forces or structures woven into reality that have no parallel in human experience. It suggests that the universe might be shaped by principles unrelated to the logic of everyday life, principles that evolved long before humans existed and will continue long after the last star fades. Standing at this edge evokes a mix of emotions: wonder, fear, awe, humility. We feel small but not insignificant. We feel ignorant but not hopeless. The mystery of the accelerating universe invites us forward, urging us to expand our curiosity, sharpen our tools, refine our questions. It is not a barrier but a doorway. Every unanswered question is an invitation to think deeper. And yet, the emotional weight of this mystery is undeniable. There is something unsettling about realizing that we do not fully understand the force shaping the destiny of everything. The galaxies drifting apart are not just distant objects. They are chapters in the story of existence itself. Their accelerating motion is like a warning written across the sky. The universe is not as simple as it once appeared. It is alive with unknown influences, governed by rules we have not yet deciphered. Physicists often describe this moment in human history as a crossroads. On one path lies the possibility of new physics, ideas so bold and transformative that they could redefine our understanding of reality. On another lies the possibility that our assumptions are flawed, that the universe is revealing the limits of human perception. Both paths lead into darkness. Both require courage. Imagine humanity standing at that crossroads, holding a torch of knowledge whose light flickers against the cosmic void. We do not know which path is correct. But the light we carry, however small, is precious. It is the product of thousands of years of curiosity, experiment, failure, and triumph. And now that light is pointed at the mystery of acceleration, illuminating the unknown in faint, trembling outlines. Somewhere beyond the horizon of understanding, dark energy, or whatever phenomenon drives the acceleration, waits like a hidden mountain range still obscured by fog. We can sense its presence. We can measure its effects. But the mountain itself remains invisible. It is as if we are exploring a landscape at night, guided only by echoes and shadows. The edge of human knowledge is not a place of despair, it is the birthplace of discovery. Every major shift in science began at this edge, the moment when the known world ran out and the unknown world beckoned. The accelerating universe places us at such a moment, urging us toward ideas that could redefine our place in existence. This feeling, of standing on a precipice looking into a cosmic abyss, has always shaped human identity. It reminds us that we are not masters of the universe but students of it. That our greatest strength is not certainty but curiosity. That the universe is not obligated to reveal itself quickly, and that mystery is not a barrier but a companion in the search for truth. The accelerating universe may be one of the most profound invitations humanity has ever received. An invitation to push beyond the known, to rethink the fundamentals, to question everything, from gravity to time, from space to existence itself. It is a challenge written in starlight, an open-ended riddle carved into the geometry of the cosmos. We stand at the edge not knowing what lies ahead. But the edge is where discovery begins. And somewhere in the depths of the accelerating universe, the next great truth is waiting, silent, patient, and unimaginably vast. The accelerating universe feels less like a discovery and more like a quiet warning etched into the fabric of space. As galaxies drift away faster and faster, the cosmos seems to whisper that our understanding of reality is incomplete. It is a message carried across billions of years, urging us to recognize that the rules we rely on may only describe a fraction of existence. Imagine standing beneath the night sky, watching distant galaxies slip farther into darkness. Their motion is not gentle, it is urgent, insistent, accelerating as though pushed by an unseen hand. This behavior forces us to confront a possibility both humbling and unsettling. The universe is not obeying the laws we thought governed it. Something deeper, older, and hidden is shaping its fate. For scientists, this realization feels like reaching the edge of a map. The familiar territory ends, and beyond it lies an expanse marked only by mystery. The equations that once explained everything now feel like incomplete sketches. Each new observation tightens the tension between what we expect and what the universe actually reveals. This tension is the warning. The cosmos is telling us that our understanding must evolve. As the expansion accelerates, more of the universe slips beyond our reach. Eventually, distant galaxies will disappear completely, their light lost forever. The cosmic stage is dimming, one horizon at a time, reminding us that there may be a finite window in which we can decipher the universe's true nature. And yet, within this warning lies wonder. The acceleration invites us to question our deepest assumptions, to search for new physics, to imagine forces and structures beyond our current grasp. It challenges us to expand the boundaries of knowledge while we still can. The accelerating universe is not threatening us. It is calling to us, quietly, urgently, saying one final thing: look deeper. The answers are hidden in the dark,